Okay, so today we're going to go ahead and take one of the conic slices, the parabola, and just elaborate on that. And I actually want to start off with kind of a little game here. Okay? So here's how the game works. It's a very simple game. And you might want to take notes on this game, but it's more important that you take notes after the game at least. Okay? So if you want to take notes during the game, that's fine too. But here's how the game works. I've drawn a point and a line here. And your job is to come up and you're supposed to add to the whiteboard a point. Okay, so that's all you're allowed to draw is a single dot. And here are the rules of the game. You have to draw a point that you believe is the same distance from each of these. Okay? So I'll actually start the game. Okay? I'm going to choose the most obvious point. This point is, you could say, the same distance from both red objects, and it goes right there. I choose this one because I believe this distance and this distance are equal. Okay, now I'm going to popcorn that to somebody. So let's have Jace come up. Grab the green marker, now the point. Show him the two congruent segments. There are actually an infinite number of these. So there's plenty of them. Okay, so the top segment you drew is correct. Stand aside so people can see. The top segment he drew is correct. He's measuring the distance between his green point and the red point. But the second segment, the bottom one there, that's wrong because you're not measuring to the line, you're measuring down to the bottom of my green segment. So how do you measure from his green point to the red line? Okay, so go ahead and redraw that bottom segment. There you go, and I would say those are the same. That's actually really good. It'd be nice if you had a ruler though, right? You could kind of see how well you did, measure the two greens, see if they're the same. Okay, so I'm just going to draw that point a little to the, so right there is where you drew. Okay, good. So you erased that. Very good. Next is, you popcorn that to somebody. So who do you want to go next? Stein. Which Stein? You got two Steins.
Both Steins.
All right. Yeah, welcome to my world. How to not block a projector while teaching. Did I tell you about the professor I had? Everything was projected onto his chest. Oh, I got to tell you that story. I'll pause the recording in a minute. Yeah, it looks a little closer to the red point than it is to the red line.
Yeah, I know. It's supposed to be, it should be about right there, probably.
So further to the right? Okay.
Whatever.
Well, it's not whatever. The rules are strict, right? The rules are very strict. You cannot break the rules. So you're supposed to really try and make it look the same. You guys think his two green segments are the same? Close enough. I think so too. Okay, so good job. Right about there. Okay. All right, we can keep the green segments going if we want to. Notice that when we measure from a point to a line, we always measure in a perpendicular fashion, right? So we've talked about this before, I think, or at least your geometry teacher should have. If you're in an earthquake, right, and you're standing, let's say, near a wall, so here's your shadow on the wall, okay? And let's say that the safest place to be in an earthquake is near a wall. You would run straight towards the wall to get there the fastest, right? So you wouldn't run over here to the wall or run this way to the wall. You'd run straight at the wall. So in geometry, we define distance from point to a plane as the shortest distance. So the example would be, I'm standing here, earthquake happens, I need to find a wall. I'm not going to go to that wall, that wall, that wall. I'm going to go to the whiteboard. And I'm obviously not going to run to this part of the whiteboard. Okay? I'm going to go the shortest possible path, right? So if somebody were to ask me, how far are you from a whiteboard? would say about a yard. I wouldn't say 4 yards, because I'm going over there. You wouldn't do that. You go with the shortest distance, right? So in geometry, we always measure from a point to a line or a point to a plane using the shortest possible perpendicular track. Yeah, you knew that, but let's try some more points. So popcorn net. Who else is coming up?
Dana.
Okay, so add a point. Sometimes you can't tell if you did it right until you draw your segments, and then you say, oops, one's a little too short. And you can just fix it. So I say just start drawing and try to fix it if it's wrong. And it's harder than it looks. That's okay, she'll step away in a minute. Okay. Keeps erasing my point. Don't do that. I'll just make it bigger. Okay, good. So that's right. Good job. And it's bothering Jace that it's still on there, so we're going to erase it. All right. Next. Who's next?
Mini sun.
He's ready to go. You guys are twins, right?
No.
No, not twins. Who's older?
He's younger.
He's older by 15 months.
Wow, that's so exact.
So almost Irish.
It is
Almost
exactly
Irish
15
twins.
months. His birthday is June 15th. Mine's some other 15th.
Your mom your birthday.
Almost Irish twins. Meaning born in the same year.
Oh, it's not quite. It has to be further out.
Just fix it. Make it further out or lower down. Choose one.
I mean, come on.
Why don't you
I think it's too.
I'm a very bad artist.
How do you fix it without starting over? That's pretty close. Maybe a little more to the right.
Let's just go with it.
No, we're not going to go with it because these points are very specific, right? There's no leeway on them. They're either going to obey the rule or they aren't going to obey the rule. If they don't obey the rule, they're called a set of points. If they do obey the rule, they're called a locus of points. So they have to obey the rule. Okay? We're going to give them a name in a
I
minute.
think that's pretty close.
I think it's pretty close. Yeah, I think I even have a really cool little ruler tool here. Let's see. Where's my ruler? I haven't been a smartboard user long enough to find my ruler. Oh, here's a compass. Ah, ruler. Let's see how I did. I don't even know how to use this thing.
Rotate.
Rotate. How do you rotate it?
Probably.
Ah, this thing's lame.
Wait, hold it down and then try rotating it.
Yeah.
Wait, hit that little square.
Right here, I think there's a circle.
This handle? This just shrinks it.
Oh.
Wait, press the little arrow thing. Where's the arrow thing?
That little arrow should do it.
Wait, are you gonna pause it? You're gonna.
No, we're just having fun with the ruler on YouTube.
No, didn't you have that like story though? that
No,
you wanted to
later.
tell us?
We're trying to.
Oh, man. All right, so much for that. Oh, I got my handle back. Let's make it really big, and maybe this little thing will work. Oh, this changes the scale between metric and standard. That's kind of neat. Except I have to measure everything sideways. That's kind of lame. I don't know. I say goodbye, ruler. All right. I think it's pretty close, Jack. Pretty close. I got to find it. Did you guys notice that these points actually are forming a shape?
Yeah.
Parabola? Okay. Now, it's possible it's a parabola, right? I mean, we haven't proven it's a parabola, but so far it seems to be forming a parabola, right? So how do you prove something like this? Like, how do you prove that this is a parabola? What you do is you start with probably an x and y axis. So you have some rulers in place. Then you pick a random red line and a random red point, and then you basically construct, using distance formula, two congruent segments. I'll show you how we do that. Watch. So we're going to take it from this really generic blank piece of paper kind of thing. We're going to take it to an XY axis plane. So go ahead and draw a Cartesian plane there. Now we're note taking. Obviously this is x-axis and y-axis. Just for the sake of convenience, we will make our directrix directly on the x-axis. So make that line red. Okay, that I know how to do. And I know it's supposed to have arrowheads on both sides. I just haven't learned how to do that yet. Here we go. There we go. This is now a line, not a segment. Red line. Okay, red line, arrowheads on the ends. We need a point, so let's see. I say we put it on the y-axis for our first one. We can always do right shift, left shift, up shift, down shift. We know how to use transformations. So let's go ahead and pick a point on the y-axis, say here. Okay, so this is our line, y equals 0. This is our point, and we'll just call it F for fun. And we'll in fact give it coordinates 0, n for fun. I would use FUN, but I'm pretty sure U is 0, so I'm going to put FON. Fun today is spelled FON. Okay? Just put it there for fun. I could put it anywhere I want, but for convenience, I'd like something to be 0. So right on the y-axis there. And now, where is my first green point? Well, the one we probably would think of first is this one. If this is tracing out a parabola, it's probably the what? The vertex. Right. So we don't need to label it V. We're not quite ready to even say this is a parabola. But let's go ahead and draw at least a curve and pretend that that's sort of the vertex. Right? Okay, now we're going to pick a random point on the curve. Maybe that guy. And let's label it P, comma, XY. And what was the game again? Try to make the what? The green point the equal distance to the two what? Red things, right? So our job is now to see if this segment and this segment are the same. So I think I need one more point down here on the red line. I'm going to pick this point just for kicks. I'm going to call it K for kicks. And the y coordinate is definitely 0. As for, I don't know, for x coordinate, let's just put x, I guess. After all, point P is directly above it, and we used x for that x coordinate, so let's try to keep that consistent. Okay, I would like to now force the two black segments to be congruent. I want to force it, because that's the game. All right, so here we go. We're going to force FP to equal PK. We're going to make it happen. How do you measure between 2 points like this on an XY grid? What's the formula would be most appropriate for this? Distance formula. So I need a big fat square root of something squared plus something squared. And on the other side, a big fat square root, something squared plus something squared. Can you fill in the blanks for me? Okay, so I'll get you started if you're stuck. If you're going to measure the distance between F and P, you subtract the x coordinates, right? So you're going to basically be using this x and this x, right? So you're going to be doing either x minus 0 or 0 minus x, your choice. So I'm just going to use x minus 0 right here. X minus 0. And that's squared. And then it's plus. And then I'll do the same thing with the y's. So we're going to do the y coordinates now. So now you're doing y minus n. Okay, now do the same thing with the other black segment. Okay, so I got you started there. You can cancel the square roots if you want. There's one on each side, right? Good riddance to that. Okay, so let's go to Jessica. So what goes on the right side here? Yeah, x minus x. Good. And? Yeah, 0 minus y or y minus 0 doesn't make any difference. That's the nice thing about this form. If you get your coordinates backwards, it's pretty forgiving. All right, so we end up with this statement. X squared plus y squared minus 2yn plus n squared equals y squared. I've already canceled the radicals. Okay? So there is no square root on the right. It is just y squared. Notice that the y squared cancels out by subtraction, leaving us with the equation of what must be a parabola. If you isolate y, you actually get 1 over 2n x squared plus 1/2 n. Now you might say that does not look like a parabola equation. Well, you haven't put in an n yet. Somebody say any number for n. 3. I heard 3 first. Y is 1/6 x squared plus 3/2. Give me another n.
16.
16. Nice. Y equals 1 over 32 x squared plus 8. You said 16. It's a parabola for sure. What we don't know is the vertical shift or the vertical dilation factor. In other words, it seems like there's an n in the answer, but it does have at least the x squared look to it, doesn't it? And depending on how n is adjusted, you will get a different parabola. Obviously, if I took this point here and pulled it down, if I pulled the point fawn down, right, what would happen to the green point? It goes down too. It has to maintain halfway between the red and the red, right? So that would move down too. Also, the shape would flatten out and look like a wider parabola. If, on the other hand, you grab the red point and pull upward, the vertex will move upwards accordingly, and it would actually look, I believe, more narrow looking. Okay? Those are just things you can think about later, but I'm pretty convinced it's a parabola, right? Okay, so let's take this now and let's talk about what we're going to do for flashcards. Okay? So you guys are going to be putting together a flashcard. Okay? And on the flashcard, you're going to have a diagram of a parabola. I think you should draw it sort of diagonal. There's no reason why you should always have your parabolas pointing straight up and down. There should be a directrix line. There should be a focal point. These all have names. So this is what's going to go on your flashcards due next Friday. Okay? Every conic will have one. I'm helping you draw your first one, so you know my expectations. This has a name. It's called the focus. There's a reason for that name. We'll talk about it later. This line is called the directrix. The actual parabola is the curve. This point, you might think is the most important point in the whole wide world, the vertex. Actually, I would argue that the focus is more important than the directrix. Focus is more important than the vertex because actually we wouldn't even have a parabola if it weren't for the focus and the directrix line. Remember the game, we started with the focus and the directrix. The parabola was an afterthought, right? The outcome to the game. But the game started with the focus and directrix. Interesting. Maybe vertex isn't so important after all, right? And this distance is called A from here to here. It's also the same distance, of course, from the vertex to the directrix line. So everything kind of has a name. Vertex does have special coordinates. We call them HK. There's also a line running down the middle that you probably know about. That's called the axis of symmetry. Boy, we used to think that thing was so important. And it is. It's pretty cool. Not as important as the Directrix. Directrix is one of the founding shapes here, right? And then the last thing you probably should draw is brand new for everybody, and that goes right here. Watch close. Nobody in this classroom has seen this before, I don't think. Right here, there's another segment. Has anyone ever seen this segment before? Let me clean this up a little bit. That segment, what is that blue segment? That's new. It's called the lattice rectum. Lattice means sideways. It runs sideways and parallel to your directrix. That's brand new, I think, for everybody. And it has a very important length, 4A. 4A. I think this goes on your note card, all of it. Not for long. Well, okay, there's the front side of your note card maybe. That says new, lattice rectum. And I think you should draw it tilted so that you don't think they're always like standing straight up and down, you know? That's not true. If they're a slice off a cone, then they can aim any direction at all in space. All right, I also think you should give this thing a definition.
Wait, does that mean it's not a function anymore?
Right. In geometry, we didn't talk about functions because everything could be turned sideways and everything was still congruent. Right? You do boxes and squares and shapes. This is a geometric shape called the parabola.
So it doesn't matter.
It's a set of points that obey a certain rule. And you can tilt it however you want. For convenience, we often will stand it straight upright and stick it right on an XY axis so we can measure it with the two rulers, X and Y, you see. But let's not overrate that. Like, that's just something we can do, but we don't have to do. Okay? All right. And some of our parabolas will be completely sideways, as we'll see. The other thing I think you should have on your note card is the definition we created. What exactly is a parabola? The parabola is the set of all points that are, now don't shout this out, I want an adjective here that means same distance from a, then I want two nouns, blank and a blank. And we're going to fit more on the back of the note card too, so I'm going to shrink that in a second. But set of all points that are blank from a blank and a blank. It's like wacky Mad Libs, except I want mathy, not so Mad Libs. I want the right words in the right spots, please. Don't make up your own adjective. Parabola set of all points that are
Crazy.
happy and from a cow and a horse. Don't do that. What words do you think would go in here? Think about the game we played. So what would be a good word for same distance? Equidistant would be a good word to put here. Nice adjective that says that. From a blank and a blank. Point and a line, correct. So, and these are a fixed point and a fixed line. You cannot change them once the game begins, right? So we're going to put fixed point and fixed line here. There's your sentence. That's definitely going on your note card because that's how the game was played, remember? What else needs to go on the note card? You also need to put some formulas on here. So I was going to try to keep my note card big and put my text smaller, but I don't know how to do that. Okay, anyway. Also on the note card, see if you can find a three-sided note card somewhere in the store. That would be cool. Three-sided note card. Anyway, this goes either on the front or the back. I don't really care. If this happens to be on an XY plane, which is highly overrated, but let's just say it was, and your directrix just happens to be horizontal, which doesn't have to be the case, and your graph looks like this, then your equation will be the following. X minus h squared equals 4a times y minus k. Now this is if. There's a lot of ifs here. This is if you're on an xy plane. This is if you happen to have a horizontal directrix. Okay, so don't overuse this thing. It's only in this particular situation. And the parabola can open either up or down for this image, okay? So let me go ahead and give you two sample drawings. Either that one or the upside down version of it. Can I just flip this thing over? Flip, there we go. So either of these pictures, you use that red, blue equation, okay? All right. Does anybody remember the equation we actually used when the parabola is sideways? Or can you just use your common sense? What would happen if I drew everything completely sideways? Actually, I don't even have to redraw this. I can just use my cool flip feature. So let's do V1. This thing needs to be, oh, that didn't work. I need to flip it upside down. I'm going to rotate it. There we go. That's what I needed to do, right? Okay, so let's say it's opening that way or sideways, the other direction. So let's say it's pointing to the left. So these are two other possibilities. For that, you're going to use this equation instead. Well, can someone guess?
Parentheses y minus h. Parentheses square equals 4a. Parentheses x minus k.
Like that?
No.
Okay, you're very close.
No. The h and k switches.
Okay, so you always want to keep the h and the x together. Okay? And you always want to keep the y with the k. So we're actually going to make sure it's y minus k and x minus h. But you're right to switch the x and the y around. Okay, that is totally correct logic. When you invert in mathematics, right, you switch x with y. That's the whole thing, right? That's the whole point. Everything ends up reflecting on the y equals x line. That's this line here. And everything looks sideways. Right? Okay, so good. Yes, and that's the right answer. I think you need these equations. And you need context for them, right? You need to say, look, I'm going to only use this when my directrix is horizontal. I'm only going to use this when the directrix is vertical. You know what I mean? So don't use them at the wrong times. That's one of the biggest problems with math students is they just use formulas randomly. They don't have any context or rules about when they use them. There are many other formulas I could give you, but none of them are necessary. These ones are necessary, unless you want to rederive them with that distance formula every time. Okay, let's go and look at some examples real quick. So let's say I told you, given the directrix is the line y equals 12, and the vertex is negative 610. And then I want you to find the equation of the parabola. Now you might think this is not enough information, but go ahead and draw what you think this means. And you'll see it is plenty of information to answer the question. Your final answer will either look like this, or it will look like this. I'm not going to tell you which one. You have to figure that out. So first sketch the givens. Ask yourself which of these two makes more sense to be using, and see if you can fill in A, H, and K. All right? Give that a try. I didn't even see how much time I have left for my class period. All good. 20 minutes left. I was going to do 3 examples today, so we should be good. Let you guys learn it by solving it yourself. Okay, so when you draw, you get a much better feel for things. This is the line y equals 12. right? And then the vertex is over here at negative 610. So I think your parabola pretty much has to open downwards, doesn't it? There's really only 4 possibilities. And you'll notice that the parabola never opens in such a way as to hit the directrix. It doesn't ever hit the directrix. It always avoids it, kind of like an asymptote, but it's not an asymptote. So there's your graph. And so now we already know that we're going to be using which form? The one with the y squareds or the one with the x squareds? You're going to want to use this one. So remember with me, all year long we've been doing parabolas, and the x has always been squared, and the graphs have always opened up or down. Correct? The whole year we've been doing parabolas that open either up or down, and they've always had x squared in their equation, right? The y squared ones are clearly for something else, sideways stuff. Okay? So graphs open right or left. Okay, so anyway, we're definitely going to settle that one. I think h and k were given to us on a silver platter. Weren't they? Coordinates of the vertex. Okay, so that's good. So we can update our equation. X plus 6 squared equals 4a times y minus 10. How many of you got that far? Good. And then when it comes to what is a, that becomes a question of, do you know what a means? Okay? Now a is not the same thing as we learned earlier in the year. Y equals ax squared plus bx plus c is a totally different a. It is not the vertical stretch factor. Okay? So it's actually a different thing. It's a geometric measurement. It is literally the distance from here to here. That's a. So how far is that? That's pretty obvious. Yeah, now some teachers will give you a formula for this sort of thing, but I think that is a complete waste of time, memorizing formula for this. Look, you're at the point negative 610. You go up 2 spaces and you hit y equals 12. How is a not 2? Well, some people say, well, a is negative 2. Fine. I'm going to say a is 2. I'm going to stick it in right here. Okay? And once I write my equation, I'm going to have this. And there is something that's a little bit off about this equation. This doesn't tell me that it opens down, you see. So I'm going to go ahead and add in one more little feature, a negative right there. It's just to make sure that my graph opens down and not up. I always do that as an afterthought. Some people memorize rules like if the directrix is above the vertex, then the a is negative. And if the directrix is below the vertex, then the a is positive. I don't like memorizing rules. I like to just understand things. So the cool thing about this is that it's so easy to graph when you're given this equation. So now you can give this to somebody, and if they know how to treat the numbers, they would know exactly what the 6 means, exactly what the 10 means, exactly what the 8 means. They would even divide that 8 by 4 to figure out the gap here. Okay? So this is called a standard form of parabola. And so let's go back a page, and right here, let's title these standard forms. Okay? These are the standard forms. And somehow you're going to fit all of this on 2 sides of a note card. Every conic has a game. Listen, every conic has a game. Okay? Every conic has a definition. Not too different from this sentence I just wrote. And every conic has its own set of equations and labels. All right? So just be ready to do this exact same thing when we hit the ellipse, the circle, and the hyperbola. We're going to repeat all this. Let's try another example, though. How would you handle this one? Given the vertex is at negative 610, the directrix, the focus I mean, is at negative 510. Try that one. Same instructions. You're just trying to create a standard form equation. So you're still going to have to decide if you want this one or, I don't know why I put a 10 there, there's H there. Do you want this one or this one? So don't shout it out, let people think, draw and think. One of these is appropriate, and you try to fill it in. Okay, so we need to draw it, right? This time you have 2 points, so don't draw any lines. So you have, switch back to black here. So you've got the focus point at negative 5, 10. So that's here. And then the vertex point at negative 6, 10. So now you can see that the focus, remember the focus actually is sort of inside the bowl part of the parabola. So I always think of the parabola as a bowl. And inside is a piece of fruit. Okay? Which means you'd have to draw it this way. So the fruit is the focus, see? And the bowl is the parabola. You know, it's got the word bowl in it, kind of. And so it's got to open to the right. There's no other way you could draw it. If you draw it any other direction, you run the risk of having nonsense here. So it means your directrix is clearly in the back somewhere, probably just over at negative 7. Everything's just spaced by 1s here. Okay, you really don't need the full picture, but at least something like this. And then you just need to make your decision. Which standard form should I use? Is it the x's that are squared or the y's that are squared? Yeah, see how the graph is opening to the right? That's brand new. We have not done that this year at all. So we're going to actually choose this one this time. No x squareds. And then we're going to put in the h and the k. Those were freebies. So y minus 10 squared equals 4 times a times x minus h. In other words, x plus 6. A is this little gap, remember? Right here. So how far are those 2 points apart from each other? It's pretty obvious. Just 1. Now, does this object open like backwards? Or should I keep things positive? We're going to keep A positive. The only time you use A is when the graph either opens down or to the left. Okay? In fact, let's go back to our note cards explanation. And let's just put that in here. So use a negative A if the graph is leftwards or downwards. That's the only time you ever use a negative A. Okay? But don't forget to do it either. Obviously that's important. It's just, I usually think of it after the fact. So use a negative A if left or down. Okay, now you know exactly what to put on your first note card. You've seen 2 examples of how to use it for the homework this weekend. Let's do one more here. This is my 3rd example. The directrix is horizontal. Okay, that's the first given. The vertex is at 2, negative 1. And it passes through 1, 1. The parabola literally passes through 1, 1. 1, 1 is one of the points on the parabola. So see if you can sketch this and come up with an equation. When you're done, see if you can find the following. Okay, so first thing you do is a sketch, a standard form, but then let's take it beyond that. Let's find the focus, since it's not actually mentioned. So you can find the focus. See if you can find the intercepts. That means x and y intercepts. See if you can find the equation of the line of symmetry. The equation of the directrix. The endpoints of the latus rectum. I'll shrink all this so you can see it. There's so many things I could ask for. And by the way, if you ever see the word analyze, it means find everything. Okay, let me go back up so you see my givens one more time. This is the problem. All you know is the directrix horizontal, you know where the vertex is, you know it's passing through 1, 1, and there's a lot of things to find. If I don't finish this example by the end of the class, I'll just record the ending of it during 6th period and post it. Okay? But you can also work on it yourself. I'd rather you try it. Okay, so the givens are that you have 2, -1 as a vertex, and 1, 1 as a point that the graph passes through. So your parabola actually looks like this. So what's missing from this problem is any information about directrix or focus. It doesn't seem to be given at all. Okay, so what you need to do is just realize, look, this thing is definitely opening upward. So I'm going to definitely be using this equation just because it looks like it's opening up. Then you're going to plug in anything you know. So, for example, you know that it passes through 1, 1. You could actually use that as an x and a y. These are a valid x and valid y to satisfy the equation. So let's put in a 1 and a 1 for the x and y. H and k were given to you on a silver platter, right? 2, -1. So you can plug those in. So you get this equation. 1 minus 2 squared equals 4a times -2 minus 2. Oh, I switched these around. This is the positive one. This one's the -1. I don't know why I wrote 2 minus 2. I meant to write just 2 here. So I got a equals 1/8, and that's a start. So now we know that our function, or our equation of a parabola in standard form is, let's put in all of our values. We know that h was 2, and we now know that a is 1/8, and we know that k was -1. So here is our formula for the parabola, 1/2 y plus 1. Okay, hang on to this. We're going to use it to answer lots of things. And let's just take a quick look at the questions. So we already did the sketch. We already did the standard form. Now it's time for the focus. Well, the focus is going to be 1/8 of a space above the vertex. So it's going to be inside the bowl of the vertex, and it'll be at 1/8. So basically, let me see if I can show that here. It's going to be just above the vertex. All right, so let's just draw an enlarged picture. Okay, so if this is our vertex at 2, -1, and you go up 1/8 of a space, this is going to be at the point 2, -7/8. Okay, so your focus is at 2, -7/8. Okay, next is just peeking. Intercepts. Okay, intercepts. So to find the x-intercept, let y equal 0. So it's going to look like this. X minus 2 squared equals 1/2 times 0 plus 1. In other words, x minus 2 squared equals 1/2. And if you solve this, you get 2 plus or minus root 2 over 2. Okay, so I'll leave you to solve it, but you get x equals 2 plus or minus root 2 over 2. Okay, those are your x-intercepts. Let me move this out of the way real quick. That was how I found my focus. Okay. Let's do our y-intercept right next to this. So with the y-intercept, we let x equals 0. In other words, it's going to give us 0 minus 2 squared equals 1/2 times y plus 1. In other words, 4 equals 1/2 y plus 1. If you double and subtract 1, you get y is 7. Y is 7 is the answer. Okay, pretty easy. The next question, let me peek. Okay, the question is asking for the line of symmetry. Next, line of symmetry and the directrix. Okay, line of symmetry passes through obviously the vertex. So this is the line x equals 2, because this vertex was, remember, 2, 1, 2, negative 1. Okay, then the directrix we could have done earlier. Here's your curve. We already said that the focus is 1/8 of a space above the vertex. So the vertex is the black dot, 2, negative 1. And that puts the directrix 1/8 of a space below the vertex. In other words, at y equals negative 1 down an eighth. So negative 1 and 1/8, or you could say negative 9/8. So y equals negative 9/8. So that takes care of these two. And lastly, the endpoints of the latus rectum. Okay, let's go down. Endpoints of the latus rectum. Okay, so this is new for everybody. Here is, oh, by the way, I will call the latus rectum the LR, okay? Okay, so here is your graph, here is your vertex, here's your focus. The latus rectum is a brand new segment. It runs sideways from parabola to parabola, actually, and it passes right through the vertex. It is parallel to the directrix, and it has a length of 4a. That's very important you understand that. 4a, which, if I zoom in, would look like this. There's vertex. You have 2a on this side, and 2a on this side, you see. All right, but a was 1/8, so basically it's a quarter space on either side. A quarter space on either side. So 2a is 1/4, you see. So this is a 1/4 and this is a 1/4. That's 2a and 2a. Okay, remember that this is the point positive 2, negative 7/8, right? So if you want to shift, let me clean that up. If you want to shift left and right from here by a quarter space, you would just do that simply by adding and subtracting 1/4 from your x. Okay, so your answer is going to be, your answers, endpoints of the latus rectum are 2 points. They both have a y-coordinate negative 7/8. Two minus 1/4 is 7/4. 2 plus 1/4 is 9/4. And that concludes our first lesson on parabolas. Actually, we probably will just move on to the ellipse. The next thing to really discuss is how to complete the square, but we can hit that all in one day and talk about how to complete the square for any conic. So, all right, see you Monday.